Well, our next presentation is by our good friend Douglas Mather. So he's a consultant from Mather Power Analytics, and he's gonna present today secondary arc modeling for single-phase auto-reclosing in EMTP. So welcome, Doug. Thank you very much for coming.
All right. Thank you, David. Okay, maybe I'll just put this here for now. Does it fit? Maybe not, huh? No, okay, it doesn't fit, so no problem. I promise I won't tell him the accountant jokes, right, Jean? Okay, so over the course of the classes that Jean and I give quite frequently, we get asked about arc modeling, particularly arc modeling in air. How do I model the arc, for example, from a disconnect switch that opens under load? And this particular exercise here is a similar exercise about secondary arc. The bottom line is this is not an easy topic to teach or to model because, again, it's a challenge of getting data. So there are some papers in the literature that do discuss this. So let's talk a little bit about just a background about what is secondary arc and why we're concerned about it. Why do we do single pole reclosing in EHV systems? And then we'll talk a little bit about the mathematics around the concept of arc modeling. And then we'll do some EMTP model examples. So how many folks here have experience with single pole reclosing? Anybody? Single pole tripping on EHV lines? One or two, good. So single pole tripping really had its origin, again, in the province of Quebec. A lot of stuff comes out of the province of Quebec.
We don't do anything.
No, because you don't. But single pole tripping was really something that came out of Shawinigan, the Shawinigan system. The folks who started Shawinigan Engineering, Andy Sturton, wrote a lot of the initial papers on this topic. And the concept is, in certainly solidly earth EHV systems, most of your faults are single phase to ground. And most of them, of course, are temporary. And again, we're talking about EHV systems in particular, where you have long air gaps, and you're not talking about a lot of permanent faults. So single phase fault clearing, opening only one pole of the breaker, the faulted phase, and then reclosing after an appropriate period of time, can improve reliability and lower the risk of system instability because you're not clearing all three poles of the line. You have a temporary unbalance that you have to take care of while the phase is open, but it's a very useful technique to use. The concept of secondary arc, however, puts the successful reclose at risk. So, what is secondary arc? So you have a heavy fault current producing an ionized channel from the power follow arc on the faulted phase, and that remains momentarily. You have a momentary ionized channel after the power fault current is terminated. The circuit breaker is opened. And the capacitive coupling from the live phases is a driving force or driving function to maintain that arc in that ionized path for a certain period of time. It usually extinguishes itself, but if you reclose before extinguishing, then of course you will reestablish the fault and have an unsuccessful reclosure, and the whole line will trip out. So the challenge then in applying single pole tripping is to make sure you're waiting long enough to ensure that the secondary arc has been extinguished. And there are techniques, of course, to detect the extinction of secondary arc by simply looking for the voltage to reappear, the capacitive coupled voltage on the phase. But again, the battle you're trying to fight is reclosing too soon versus the prolonged delay and maintaining that unbalance in the system. And that can have an adverse impact in and of itself if you're waiting too long. So if we know then that secondary arc is a function of capacitive coupling, we know that heavy conductor bundles, close compact lines, can have a higher level of secondary arc challenge than lines that have wider spacing, lower capacitive coupling. So the arc extinction time is then mainly a function of that secondary arc current, which is a function of the coupling. The overvoltages that happen when you reclose, you have a switching surge, trap charge, fault location, those are all important influences on whether or not you will successfully close the line back in. Again, as we said, phase-to-phase capacitive coupling is the main influence, and again, the compact lines and multi-conductor bundles. Down at the bottom here, we see the typical capacitive coupling phase-to-phase in a conventional 500 kV line is about 1.8 nanofarads per kilometer. It is significantly higher in a compact 500 kV line, getting up to close to 2.6 nanofarads per kilometer. That's the phase-to-phase coupling. So modeling of secondary arc in EMTP is a challenge because the interaction of the line and the arc has a lot of random properties associated with it. A lot of factors, including the dynamic characteristics of the arc itself, with the impulse currents going through it. You have dielectric recovery properties of the air channel, and that is influenced very much by the thermal buoyancy. The arc is going to try to rise due to thermal buoyancy, and the wind is going to blow the arc horizontally from its position. And of course, there are electromagnetic transients that are associated with all of that. So the specific arc model parameters are sensitive to a lot of things. The location on the line geometry, and the length and the line voltage. And in reality, for strict accuracy, you have to base those parameters on actual measurements. So the generalized model approach I'm going to show you should be regarded as something that can be used for sensitivity analysis. It's based on 400 kV measurements that were done by some EMTP folks in Europe. But again, it's not a generalized physically based model. That's the important thing to recognize. The parameters can vary with all these factors. So the concept is that the arc column energy balance equation for conductance, the rate of change of conductance with time, right, is a function of the stationary arc conductance and an arc time constant. And so the concept then is to evaluate that arc conductance that's being driven by the capacitive coupling. Now, this is only looking at thermal reignition. It's not looking at dielectric. So we have to add dielectric effects separately. So this is the equation. And again, this is based upon a power system computation conference paper that was done a few years back by Kizelkai and his colleagues. And they implemented that model in ATP models. So what I've done in this exercise is to implement the same model in RV and then to add some things to that around dielectric breakdown. So the arc time constant here is inversely proportional to the arc length, and it's given by this equation. And that length of that arc, L subscript arc, is the time-dependent dynamic length of the arc. That's the most important parameter that's going to influence the arc extinction. And the bad news is, it's the one that's highly dependent on the random environmental factors, right? Wind, thermal buoyancy, but this, of course, is why modeling of free arcs in air is such a challenge, because of the random nature of those properties. So the specific conditions for arc extinction, you have rapid elongation of the arc by air movement. That's the principal mechanism. You stretch out the arc length to the point where it can't sustain itself anymore. And of course you get the thermal buoyancy. That secondary arc elongation is driven primarily by thermal buoyancy initially, strong upward movement due to the primary arc plasma. And again, wind comes into factor. And as you stretch out the arc resistance increases, the arc current decreases. And then when the arc goes out, you have a recovery voltage, which can then reignite the arc until it's sufficiently long that it can sustain the extinction. So then there's, when the arc extincts, when the arc extinguishes, again, you get this short recovery period where you have the high amplitude peaks that are superimposed on the fundamental AC voltage. We also have traveling waves that will occur when the reignitions take place. And that complicates the exercise as well, which is why you need a program like EMTP to evaluate that. Okay, so then you are looking for a point where the reignition voltage exceeds the recovery voltage, and the arc extinguishes. So again, here's the paper reference. It's a 2002 PSCC paper, Laszlo Priklik, Kizil, Kaiban, and Handel, improved secondary arc models based on stage fault tests. What they did in this paper is they actually did stage fault tests on a real 400 kV line, and they observed the parameters of the arc. They observed, as a function of wind, how the arc moves up with the thermal buoyancy, how it moves with the wind, how it elongates, and they developed some arc parameters as follows at the bottom. So you have the arc voltage of 900 volts per meter, 0.9 kV per meter. Initial arc time constant of 1 millisecond, the initial arc resistance of 22 milliohms per meter, and the exponent of the time constant equation, we go back here, the exponent A, or alpha, minus 0.5. And this is the time-dependent length of the arc that the authors proposed in their paper based on their observations. And there is a similar model, by the way, in the examples of the EMT folder based on a 69 kV line. Very different arc elongation parameters to this particular case where it's modeled based upon the 400 kV line observations. This is in per unit of the initial arc length, this chart. So the extinction criteria then that's used in the model that they presented is looking at the time derivative of the arc resistance, the rate of change of the arc resistance exceeding a predetermined value per unit arc length. And at the same time, the arc conductance is less than some threshold value, 20 megohm per Siemens meter. 50 microsiemens per meter is the G minimum, the minimum conductance threshold. Again, there's no dielectric restrike process here. What we have to do to simulate the dielectric breakdown is to measure the arc recovery voltage and compare that to a threshold restrike voltage, and then reset the conductance at the post-restrike value. The way that I do that in this approach is I look at a power frequency air breakdown, an air breakdown equation from the IEC insulation coordination standard. And that's a function, of course, of the gap configuration. And I use that in conjunction with an equation that's given by the folks in the paper as well, this one here, that the ES, the electric field strength at a temperature, ambient temperature TS, is approximately equal to this equation, where T0 is the temperature of the arc channel at current zero. And of course, tau is the arc time constant. And then little t in the exponent, that's the simulation time from the time that the AC power follow arc extinguishes. So it's the length, the duration of the secondary arc that's going on. Again, this is something that is not firmly established yet, but you can simply simulate that, again, by resetting that conductance down to zero. And here is the model in EMTP. We can see at the top the equation that we're simulating, We initiate the point where the power follow arc trips, so the breaker is opening at that point. And then we have the equation for the length of the arc, and we're simply implementing the equation on top in controls. And then down at the bottom left, we have the criteria that compares this, looking for the rate of change of arc resistance, comparing that at the same time to the minimum arc conductance. Over on the right, we have a calculation of this equation, where we're looking at dielectric reset, the potential of dielectric restrike of the gap after arc extinguishing. And then all of that, of course, is looking at a variable. Down at the bottom, we're using the variable admittance model in EMTP. What I can do here is stop there for a second and show you the case. What I do is I'm using the, oh, there's the little annoying thing that Jean mentioned before. I actually like that, because I'm one of those users that always forgets to save his work. Anyway, here, let me get rid of this so you can see this stuff a little bit easier. What I'm doing here is, this is the 230 kV sample case that we use in teaching the EMTP course. And here we have the secondary arc model. In two locations here. We have one on a line that's about 100 kilometers in length. This is 230 kV. So again, the parameters are for 400 kV. This is applying it at 230 kV simply as a demonstration of the concept. In actual fact, single pole reclosing is not used very often at something like 230 kV. Here's another example of a fault in the middle of this line. This line is a 200 kilometer long line, so it's twice the length. And again, here is the scripted model where we specify ambient temperature, the arc temperature at current 0 in degrees Kelvin, the field strength of the arc at T0, and we go through the arc parameters. So here is all the different parameters, including some miscellaneous parameters such as the fault duration and that kind of thing. But these are the threshold values that I gave in the presentation for the arc conductance and the criteria for extinction. If we go inside, then we see Shift I. So there is our model that I showed you on the slide. And so if I look at scope view, this one is for the short line. This is the 100 kilometer line. At the top left, we see the fault current, and we see the secondary arc. I'm going to zoom in on that for you. So we see here the arc dynamics. Right? So there's the secondary arc waveform. Only about 10 amps, driven by the capacitive coupling, and we can see the nonlinear nature as the arc length grows. We see the current peaks grow here, and then finally the arc reaches the criteria for extinction here. And that corresponds to this point in time. We see the arc voltage as the arc elongates according to this line. This is the dielectric strength line, this blue line. And here we see the arc voltage that's following the pattern of the arc length. And finally, the voltage recovers to the capacitive coupled voltage at the point where the arc extinguishes. Now if we look over at the long line, look what's happening here, see? Here the recovery voltage is hitting the dielectric strength curve. It's a longer line, right? The currents are higher. So here we see, when we look at the secondary arc, we see a period where we have the higher spikes increasing. The breaker has not closed. We're just reestablishing the secondary arc. It's flashing over the air gap, and we see the electromagnetic transients that are occurring. Like we're seeing the oscillation from the line going back and forth. So just some general guidance And then we have 5 minutes for questions if we need to, but let me go back to the presentation here. Just general practical guidance on implementing single pole reclose, just from experience. So if the ratio of the primary fault arc current to the secondary arc current is greater than or equal to 50, then the probability of a successful reclose is about 90%. That's the Andy Sturton rule, as I call it. It's possible to successfully reclose if it's less than that, but you start to increase the probability of having an unsuccessful reclosure. Deionization time, minimum primary arc deionization time, there's this cute little equation in milliseconds, 175 plus 0.5 US, where US is the system voltage. So here we have, for example, at 220 kV, we have to add 285 milliseconds to 175, and you're getting something in the order of 360 to 400 milliseconds. At 500 kV, it's correspondingly longer. Another technique that's seen out there is the four-leg shunt reactor. The fourth leg, of course, is the zero sequence reactor, and that serves to reduce the actual current in the secondary arc. And so that permits more rapid auto-extinction, so you can compensate. You see that quite often in overseas countries where reclosing like this is widely used. So I think that brings me kind of to my end, the end of where I'm supposed to be. If there's any questions about this.
Hey,
Yeah.
You said length of a line plays a major role, so it's between if you have 50 miles or 100 miles of a line.
Yeah, I mean the length of the line does matter, and
The traveling way.
well, it's traveling way, but it's also the amount of current in the secondary arc that you're driving, right? Yeah. So, and you can see that here. I mean, these are two lines of almost the same geometry, and one is taking about 0.7 seconds to extinguish the arc, the shorter line. The longer line is taking about 1.1 seconds to extinguish the arc.
That's the reason I don't elect the radios,
Yeah.
because they have open lines.
Right. Yeah.
You're talking about using reactors. I know AEP uses reactors.
Yeah, the four-leg reactor.
Yeah.
Right. Yeah. Yeah. So it's like you have three reactors to a neutral bus, and from the neutral bus to ground, you have a fourth reactor, and that fourth reactor is optimized to compensate for the line capacitance. You have to be careful when you apply that, because it can result in resonant overvoltages due to the presence of the reactor when the arc extinguishes. Okay.
Any more questions? Well, thank you very much, Doug, for this presentation.
You can have this back, and I'll.
Let's put our hands together for Doug. Thank you. So there is a slightly change on the program. So actually, the next presentation is going to be done by Derek Wesley from Mitsubishi. So welcome, Derek. Thank you.